Okay, so we're going to look at a few problems associated with the definition of the equilibrium constant in terms of concentrations for reactions at equilibrium. And just to remind you how we go about writing an equilibrium constant for a general reaction, here I've got what's called a homogeneous reaction. Okay, it's homogeneous simply because all of the substances A, B, C and D in this reaction are in a single phase. Okay, that's what homogeneous means. Everything is in a single phase, and usually everything might be in aqueous solution like it is here, or you might find, for example, everything in the gas phase. We'll see some examples of that later on. And if we have a homogeneous reaction, there's a general way that we go about writing an expression for the equilibrium constant in terms of concentrations for reactions of this sort. So what we're going to do first of all is write down Kc. That's what we're trying to determine here. And the way that we go about writing the equilibrium constant is the following. We first look at everything that happens to be a product in our reaction, and here there are two products, C and D. And what we do is we write concentration terms for both of those species. Okay, so we have a concentration term for C, that's here, and for D, that's there. What we then have to do is to raise those concentration terms to the power given by the coefficient that occurs in the chemical equation that we've got here. So you can see that species C, that's this one here, has a number in front of it, which I've represented by a letter because this is just a general term, but that will then be the power to which we raise the concentration in the expression for the equilibrium constant. Similarly, we're going to write down the power for species D, and that will be the number that occurs in the chemical equation associated with species D. Okay, so we basically write down concentration terms for the products, and then the bottom we write down concentration terms for the reactants, in this case A and B. And again, we are going to raise those concentration terms to the appropriate power, small a for A and small b for B. Okay, so that is our equilibrium constant expression. I haven't explicitly put in multiplication signs, but obviously these two concentrations on the top are multiplied together and these two concentrations on the bottom are multiplied together. Notice that there are no plus signs in the equilibrium constant expression. You will never find plus or minus signs in the equilibrium constant expression. Everything is a multiplication, as I've explicitly put in here now, or a power, raising something to the power. And the powers that you use, just to remind you, come from the equilibrium chemical equation, as you can see here. Okay, those values C and D for the products and A and B for the reactants. Okay, so that's my equilibrium constant expression, and that's how I go about working out what it should be. Okay, in the case of a heterogeneous equilibrium, heterogeneous means different phases, two or more different phases occurring in the chemical reaction. And you can see here we've got a chemical reaction that involves solids and gases. So this is heterogeneous. And when we write down equilibrium constants for heterogeneous reactions, we only include terms for gases or species in aqueous solution. Okay, those are the terms that we include in our expression, and we exclude anything that happens to be a pure liquid or a pure solid. But apart from that, we proceed in exactly the same way as we have before. So in this case, we look at our products. We write down concentration terms for everything that's not a liquid or a solid. And in this case, the only non-liquid or solid that we have happens to be this species D here, which we're going to raise to the power to which it occurs in the chemical expression here. Notice that the other species are solids, so we're not going to write down, or we're not going to include the concentration terms for C or for A in our equilibrium constant expression, which means that our equilibrium constant expression is just going to be as stated there. Okay, so one other point that I forgot to mention is that these concentrations that we have in our equilibrium constant expression are concentrations measured at equilibrium. So in principle we could put little EQ symbols on our concentrations just to remind ourselves that these are concentrations measured once the reaction has proceeded towards equilibrium. Okay, so bearing that in mind, let's look at some problems that we've got here. And we have some real chemical reactions that are at equilibrium, and what we're asked to do is to write down the expression for Kc and also to determine its units. Okay, so we're going to proceed in exactly the same way as I've previously outlined. We're first of all going to write down what the Kc expression will be. And first thing we're going to do is look at our products, in this case sulfur trioxide, SO3. So we're going to write down a concentration term for SO3. And we're then going to raise that concentration term to the power that occurs in the chemical expression, which in this case happens to be a 2. Okay. We're then going to divide that concentration term, and in the denominator of this fraction we're then going to write down the concentration terms for the reactants, which in this case happen to be sulfur dioxide, SO2, and oxygen, O2. Okay. The final thing we have to do is to raise those concentration terms to the correct powers. So here you can see we've got a 2 for the sulfur dioxide, so we have to put a 2 there. The oxygen doesn't have a number in front of it, so that just means it's equal to 1. Okay, and so raising anything to the power 1 is simply the same as writing the concentration itself, so we don't actually need to put 1s in here. Okay, so that would be the expression for the equilibrium constant for this reaction. A few things we could also put in if we wanted to. We could remind ourselves that these are equilibrium concentrations, and we could also put phases in, so we could remind ourselves that this is SO3 in the gas phase, SO2 in the gas phase, and oxygen in the gas phase as well, but I've omitted that in this case. So that's our expression for Kc, but we also need to determine its units. Now there are a number of ways you can go about doing this. The way that I find the simplest is the following. If we look at this expression, okay, on the top we have a concentration squared. In this case it happens to be the concentration of SO3, but whatever it is, it's squared. Okay. On the bottom of this fraction we have a concentration squared, and we also have another concentration term. Okay. And if we look at that simplified expression, which tells us the dimensions of what we've got, okay, what do we notice? Well, we notice that actually we've got a concentration squared on the top and a concentration squared on the bottom. So those two can cancel out. And if we cancel out those terms, we're left with a 1 over concentration. And another way of writing 1 over concentration is simply concentration to the minus 1. Okay. So whatever the units of Kc are, they're the same as concentration raised to the power of minus 1. Now if we happen to be measuring concentration in terms of moles per decimeter cubed, if that's our concentration units, you can see that we then have to raise those units to the power of minus 1. And so what we then do to work out the units of our equilibrium constant is we multiply the units powers by the power outside the brackets. Now here we have moles, so that's moles to the power 1, which I haven't explicitly put in there, but 1 times minus 1 is simply minus 1. So we're going to get moles to the minus 1. For the decimeters part, we've got decimeters to the minus 3, and minus 3 times minus 1 is plus 3. So we get decimeters cubed. Okay, so those are the units for this equilibrium constant expression. Okay, next example. Here we have a gas phase reaction. We've got hydrogen iodide dissociating to give us hydrogen and iodine. Exactly the same procedure as before then. We're going to write down our equilibrium constant expression, Kc. We're going to write down the products, that's H2, concentration of H2, multiplied by the concentration of I2. Okay, whoops, I2. We're then going to consider the powers. Well, here effectively we've got a 1, so we're going to have a 1, which we don't explicitly put that in there. Here we've got a 1 for the iodine. Again, we're not explicitly going to put that into our equilibrium constant expression. We're then going to divide that by our reactants. In this case, we've got hydrogen iodide. It's the concentration that we're interested in. And then what we're going to do is we're going to raise it to the power that occurs in the chemical equation, which in this case is a 2. Okay, so that's our equilibrium constant expression. Again, we could write down EQ for each of these concentration terms to remind us that it's at equilibrium, and we should also include the phases, but I haven't done so here. That then is our equilibrium constant expression for this reaction. We then need to determine the units. Well, again, if we look at this expression here, what do we notice? Well, we notice that on the top we've got a concentration times a concentration, and on the bottom we've got a concentration squared. A concentration times concentration is just concentration squared. So we've got concentration squared on the top and concentration squared on the bottom. And of course, both of these are the same, so they will cancel out to give us 1. What does that mean? Well, it means that our equilibrium constant expression has no units. It doesn't have units associated with concentration or anything else. Okay? So there are no units associated with this equilibrium constant expression. Our third example. Now, what do we notice about this equation? First of all, we notice that it is a heterogeneous expression, because here we've got solid, solid and gas. And remembering what I said earlier, we only include terms involving the substances that are present in aqueous solution or the gas phase. We don't include pure liquids or pure solids. So our Kc, equilibrium constant, is very easy to write down in this case. It's simply the concentration of CO2, and we notice that the stoichiometric coefficient here is 1, so that's going to have the power of 1, which again we don't explicitly put in. We can again remind ourselves that that's a concentration at equilibrium. Okay, so that's our Kc expression. What's our units going to be? Well, you can see here that Kc is simply equal to a concentration. So Kc will have the same units as this concentration, which is usually going to be moles per decimeter cubed. Okay, so that's our expression and that's our units. Very simple in this case. Our final example here is the chemical equation that is used to depict the formation of ammonia from nitrogen gas and from hydrogen gas. It's homogeneous, so everything's in the gas phase, and so we're going to proceed exactly as we've done before to write down our expression for Kc. We first write down our product, which in this case is ammonia gas, and we're interested in its concentration at equilibrium. And remember, we have to raise that concentration term to the power that occurs as the numerical coefficient in the chemical equation, which in this case is a 2. Next thing we have to do is to then consider our reactants. In this case we've got N2, which is also a gas, and again we want its concentration. And the power to which we're going to raise it is the number that occurs in this stoichiometric equation, which in this case is simply a 1. It's not explicitly put in, and so I'm not going to bother to put it in here. That's assumed. The final term we need is associated with our hydrogen gas. That's our other reactant. Oops, that's in the gas phase. We want its concentration. These are at equilibrium. And the final thing that we notice is, of course, that we have a 3 as a factor in this equation for the hydrogen, and so we need a power of 3 down here. Okay, so that then is our expression for our equilibrium constant Kc. We need to determine what the units are going to be, and we'll proceed in exactly the same way as we've done before. Notice on the top here we have a concentration squared. On the bottom we have a concentration times a concentration cubed, which gives us a concentration squared divided by concentration to the power 4. Now what we can do is we can cancel off some of these concentrations. We can cancel off concentration squared on the top, which means that the concentrations on the bottom becomes 4 minus 2, leaving us with 1 over concentration squared. And remember, another way of writing concentration squared, 1 over concentration squared, is concentration to the minus 2. So the units of this equilibrium concentration will be the units of concentration raised to the power of minus 2. Now, if we assume, like we've done before, that our concentration units are moles per decimeter cubed, what we have to do is to raise that concentration term to the power of minus 2, which gives us the following. We've got moles to the power 1 here. 1 times minus 2 is minus 2, so we get moles to the power of minus 2. We then have decimeters, which here is raised to the power of minus 3. Minus 3 times minus 2 is plus 6. Okay, so that will be the units associated with this equilibrium constant expression.